When implementing PID control in your microcontroller, you don't have to use all three parts of control, the P, the I, and the D. But in this part of the video, I'm going to show you how to use all three together in your equations. Whichever of the parts you don't want to use, you can simply set those parts to be equal to 0. All of the control equations in your motion control code will occur inside of a loop. The first thing you want to do inside this loop is read the current position from the sensor. In this code that I'm writing, I'll make the variables be in red. So here we're going to read the value from the sensor and we'll store it as a variable called position. The next thing that we want to do is calculate the error. The error is calculated as the difference between our target position and the actual position. We have to get the target position from outside of this loop. So I've added a line where we input the target position. This line will probably come from inverse kinematics, which you would write as equations up here outside of this loop. Next, we're going to calculate the voltage based upon this error. We'll need some other variables also in order to calculate the voltage based upon all three, proportional, integral, and derivative. I'm first going to write the equation for PID, then we'll fill in where we get these other variables from. The first part of our volts equation will be the part that is the proportional part. That is the constant Kp times the error. To that, we will add on the derivative part, which will be Kd times the change in error. And finally, I'll wrap this on to the next line so we can see it. We have the integral part. I now have to show you where each of these different variables came from. We know where the error came from, but we have to take a look at what this E last, the last error, is, how we get TS, and how we get this E sum, as well as where we should specify each of these gains for the three parts of the control. We'll start with the parts for the three gains. Those things should be set outside of the loop. So way up here, actually before we even input the target, this is where we'll set what we want Kp to be equal to. And we'll have one line for each of these. Here I'll just say that we have to set Kp, Kd, and Ki. Now, for this E last, the very first time we go through this loop, we have to initialize E last. But after it's initialized, we want to calculate it every time we go through the loop. And we want to always set E last to be equal to error. That way we'll keep track of what the error was the last time through this loop. We have to do a similar thing to get E sum. in the beginning of the code, we need to initialize eSum. And then, each time through the loop, we need to calculate it. And the way that's calculated is by taking the last value of eSum plus the current value of error times TS. Now, we still have to figure out what TS is. TS means the amount of time that it takes to run this loop, our control loop. There are a couple of ways that we can do that in a microcontroller. One way is to use timing functions to read the time at the beginning of the loop, then read the time at the end of the loop, take the difference between those, and use that as TS. Another way to do it is to begin timing at the beginning of the loop, and then at the end of the loop add in a line that waits until a specified amount of time has elapsed. And I'm going to use that second method here. I'll say wait until TS time has elapsed. And way up in the beginning of the loop, I need to say begin timing. We also then need to, way at the beginning, set what value we want for TS. We will practice doing this in our in-class portion of the PID lab. Here, we can now end the loop. We still need to set the values of these three gains. We can set a value of 0 for any gain that for which we do not want to use that type of control. For example, if we want to use only proportional control, we can simply set KD and KI to be 0 and we'll have just proportional control. The way that we set the gains for each of the portions of control we want to use is more or less guess and check. There are some better ways to find these gains if we're able to model the system dynamics of our manipulator. But we can also do this experimentally. What you would do is you would start out by setting only KP. And you would put in a value for KP and then run your positioning program and watch the response of the manipulator. You would want to continue to increase KP until there was too much overshoot, more overshoot than is acceptable. At that point, you would then add in some KD gain in order to decrease the overshoot until your response is good. If you cannot get a good response by using KP and KD, only then would you want to add KI for the purpose mostly of decreasing and even eliminating the steady state error. You generally want to avoid using KI if you don't need it to eliminate steady state error, because KI increases overshoot and can cause your system to go unstable. But in general, that's the process for how you set your PID gains, and this is how you use PID control in your microcontroller program.